Thank you for the incredibly kind and generous introduction, Miklos. It's a real pleasure and honor to be here. It's an honor to be, I guess, the final talk in the series. Thank you very much. So we have an ambitious agenda. I'm gonna get started. I'll ask, if possible, for people to hang on to their questions till the end. We'll have plenty of time to discuss things that come up in this talk. All right, so the title of my talk is A New Critical Analysis of Everettian Quantum Theory. Let's get started. So let me first say a little bit about the structure of this talk. I'm going to begin with a brief preamble, and then I'll give a summary of not one, but the several different Everettian interpretations. I'll review and maybe add some additional nuance to some ongoing challenges that the Everettian interpretations have to deal with. And then I'm going to introduce some new challenges, more or less new challenges. And then I'll end with some concluding remarks. So let me just first, for purposes of preamble, just say I've benefited from years of engagement with advocates of Everettian approaches to quantum mechanics. This talk is offered in the spirit of cooperative exploration and adventure. So although I hope this talk will be provocative, it's also intended to be respectful to all the work that's gone into Everettian approaches. My goal is to generate discussions, not end them. All right, so I'm going to begin with a brief summary of some of the leading Everettian interpretations. I'll argue that there isn't just one anymore, there's several. I will also, have a couple of interesting cartoons throughout the talk. All right, so first let me talk a little bit about the original Everettian interpretation by Everett himself. So Hugh Everett's original formulation, which you can find in the unpublished long version of his 1957 PhD thesis. That thesis is called The Theory of the Universal Wave Function. And he gives a really nice explanation of what are the problems he's trying to grapple with, and then, as we'll see in a moment, his proposal for how to address them. So I'm not going to go through this in detail. I'm just going to point out that following the terminology of von Neumann, Everett notes that in traditional approaches, at least traditional at the time, approaches to quantum mechanics involve two different kinds of processes. There was the so-called, process one, the discontinuous change brought about when an observer or measuring device makes a measurement, producing a stochastic outcome and a seeming reduction or collapse in the system's state vector. And then process two, which was a continuous deterministic evolution according to the Schrodinger equation. Everett goes on to describe the measurement problem. He employs an early version of what's now known as the Wigner's friend thought experiment. It's worth noting Wigner was also at Princeton. They certainly had many conversations, so this was probably a collaborative thought experiment. So let me just review this very briefly. According to a first, I'll call it an inside observer, the one who's actually directly looking at the system being measured, a measurement invokes process one, collapse, stochastic collapse. According to a second outside observer, someone who remains safely outside of the measurement process, you can imagine that the first observer, the inside observer, is maybe in a completely perfectly sealed box, and the outside observer is outside with no way to get any information what's going on inside the box. Well, that observer, would ostensibly describe everything happening with process two, linear unitary evolution. And of course, the result of that is not a definite outcome, but a superposition. So the measurement problem can, in one presentation, be described as the problem of reconciling these two versions of the measuring process. So Everett's proposed solution, he lists a number of alternatives. The orthodox, as he calls it, approach, Copenhagen interpretation. Bohmian mechanics existed already at this point. He talks about hidden variables approaches, including the Bohmian approach. And then he lists alternative 5, which is to abandon process one and to assume the validity of what he calls pure wave mechanics, which is just process 2, an overall state vector or wave function, I guess, for the whole universe evolving linearly, unitarily, without any statistical assertions. And with, this picture describing everything in the universe, not limited to microscopic systems, no special role played by observers. And this is how he gets it off the ground. All right, so he talks about the advantages of this approach. He talks about its logical simplicity. But importantly, he makes clear that there remains the question of whether or not such a theory can be put into correspondence with our experience. And this is going to be an important theme in the talk today. He had some engagement with Bryce DeWitt already in 1957. DeWitt was not sold on this idea. DeWitt apparently found a copy of this thesis in a library. I think it was it might even have been in I forget where it was. But he was unconvinced. He sent a letter to Everett explaining the reasons why he was unpersuaded. Everett wrote back a very detailed letter, and ultimately DeWitt was convinced and became one of the strongest advocates for this approach to quantum theory. In 1970, DeWitt wrote an article in Physics Today, which is premier sort of magazine read widely in the physics community, in which he presented the Everett approach to the physics community broadly. And this is how DeWitt described the Everett approach, that the world as a whole is faithfully represented solely by a vector in Hilbert space, a set of dynamical equations, meaning the Schrodinger equation, and for a set of operators that act on Hilbert space, a set of commutation relations for the operators. He took them to be derived from Poisson brackets of a corresponding classical theory. And then one additional postulate, which was just that there needs to be enough complexity in the world that you can decompose the universal wave function into things that resemble systems, apparatuses, and so forth. So there's quite a bit of structure here. More recently, Sean Carroll has introduced a more minimal version of the Everettian approach. In Carroll's version, which he calls Mad Dog Everettianism, take Everettianism and really take it to its extreme. All we posit is a Hilbert space. Carroll generally assumes this is actually a finite dimensional Hilbert space, although maybe it has a very large dimension. A self-adjoint Hamiltonian operator defined by a specific spectrum of eigenvalues, and a unit norm universal state vector evolving according to the Schrodinger equation, and then stop. That's the only content that he proposes as part of this interpretation. In a 2018 paper with Ashmeet Singh, Carroll describes in words what he's trying to do here. And I've highlighted a couple of statements here. The simplest quantum ontology is that of the Everett or many-worlds interpretation based on a vector in Hilbert space and Hamiltonian. The most basic description of the world is given by the spectrum of the Hamiltonian, a list of its energy eigenvalues, and the components of some particular vector in Hilbert space. Everything else, including space, including fields propagating on space, all of it is supposed to be emergent from these minimal elements. And the idea is to see how far you can take this idea. And again, all of the additional elements from related physical theories are, from this point of view, supposed to be emergent from this minimal set of ingredients. Now, this is somewhat chronologically out of order. In the early 2000s and then culminating in his really marvelous textbook in 2012, David Wallace introduces a formulation of the Everettian interpretation that goes beyond just this minimal ontology. And again, this is not chronologically in order. This came before Mad Dog Everettianism, but it's just convenient logically to explain this as in this order. The idea is that beyond the minimal ontology of the Mad Dog Everettian approach, one should also single out a preferred set of operators. For example, position operators, if you're talking about a system of particles, or local field operators, if you're talking about a quantum field theory. Or you single out a preferred set of bases, which is essentially equivalent to the first option. Wallace points out it's essentially equivalent to the first option. Under the assumption that these operators are self-adjoint, each one picks out an orthonormal basis. Or, and this one is, I guess, conceptually somewhat different, you single out a preferred decomposition of the Hilbert space into tensor factors. So if you want to talk about, say the memory register of a quantum computer, then as part of the definition of the system, you would include a decomposition of the Hilbert space into a set of tensor factors, each of which describes a two-dimensional Hilbert space describing a qubit. Okay, So this is from Wallace's book. This is just Wallace basically describing these ingredients, right? So the Hilbert space, time index unitary transformations, this is the evolution, and some additional structure in the Hilbert space. That additional structure are those ingredients beyond the minimal ontology that I introduced. Wallace goes on to justify the need for these additional ingredients. And in this talk, I'll argue that that's actually very important. It dodges some problems that I will argue are an issue for Mad Dog Everettianism. So he points out that it's essential. He points out all Hilbert spaces of the same dimension are isomorphic. We need additional structure, a Hilbert space state vector, or if you talk about the state vector up to equivalence under rescaling or phase factors, a Hilbert space ray is an unstructured object, right? And we actually want a lot of structure. We want to be able to derive a lot of structure from this ontology. And so then the second paragraph is him just laying out the different possible kinds of structure you could add. Now there's a somewhat nuanced version of this approach. This is Wallace and Timpson's space-time state realism approach. And one could argue that it's a special case of the preceding approach, although maybe that's arguable. In this case, we have a preferred decomposition of the Hilbert space. We assume a factorization of the Hilbert space where each factor corresponds to a region of 3D physical space. And then the idea is that we assign a reduced density operator, rho sub I, to each spatial region where I'm using the subscript I to denote spatial regions. And implicitly, we're using here the partial trace prescription. So you start with the universal state vector and you do a partial trace. That TR there represents a partial trace where we're tracing out everything outside of the region I. And then we end up with, in general, a non-trivial mixed state density operator for the region I. And we can do this for any region. There are regions, we can talk about subregions of regions. And this leads to non-separability. This is distinct from the question of dynamical locality, whether, say, a density operator in one region can influence a density operator in another region. The no communication theorem of quantum mechanics ensures that as long as the Hamiltonian involves only local interactions, there won't be any dynamical effects that are non-local. But because of entanglement, the density operator corresponding to a region is not determined generally by the density operators in the subregions. There is a basic lack of separability in the ontology, and that's a bullet that one is willing to bite in this approach. So I'm going to talk a little bit about old ongoing challenges. Okay. But again, I hope to add a little bit of nuance to these things. So I'm going to start with the problem of identity, and I'll explain in a moment what I mean by this. Many of the basic claims of Everettian interpretations come down to a basic metaphysical question. What is your relationship to copies of yourself in the future? Well, let's first start in a single world ontology, which is the prima facie ontology that we think we live in, or at least we thought we lived in before Everettian interpretations. In that picture, well, okay, I'll come back to that in a moment. Let me first just say, the question here at issue is whether your relationship to your future self in a single world ontology is similar enough to your relationship to the many copies of yourself in a many worlds ontology. At least is the similarity enough in all the ways that matter to Everettian interpretations. Do the future copies of yourself in an infinitely branching Everettian universe share your identity in all the necessary ways? This is actually illustrated, I think, very nicely in this cartoon. So maybe take a moment and read it. So this is, a retelling of the classic teleporter problem. Hope everybody can read this. So basically, this person on a teleporter pad is asking, wait a second, if you teleport me, do I technically die? And the teleport technician says, oh yeah, of course. This is all just for show. We've already created the copy of you. There's a copy of you with all your memories, at the desired location. All we're going to do is shine a bright light in front of you and then convert you painlessly to plasma. And then the person on the pad asks, wait, are you joking? I can't tell if you're joking. And then the person hits the button, boop. The boop is the best part. Okay. So the question is, would you get on this teleporter pad? Are you okay with this arrangement or not? Now, Wallace in his book, makes this he brings this right to the front. Yeah, he asks why you should care about your future copies and what happens to them. He says, well, an agent's future self is her future self just by virtue of causal, structural, dynamical relations between it and the agent's past self. There is, I assume, no indivisible immaterial soul which passes through my life magically makes me a single being. Right? It's the question of relations that determine that there's a relationship between me and future copies. And so he says it seems, at least to him, an Everettian agent's future copies, all the future copies of themselves stand in the same relation to her as a non-Everettian's agent in a single world ontology. He finds it hard to see why in the Everett case she should regard his future self as any less me, just because there are multiple future such selves. And ultimately, you either believe this or you don't. But if you don't, it's kind of hard to get some of the crucial arguments, for example, the rationality axioms that Wallace employs in his proof of the Born rule. It's hard to get those off the ground. Right. So for example, elsewhere in the book he writes, so a bet, for example, a bet made by you is just as meaningful in the Everettian as in the non-Everettian context. Its metaphysical status may be different. In buying a bet, you're purchasing awards for some but not all of the future versions of yourself, rather than purchasing the possibility of award for your single future self. But operationally, the process is the same. Okay, so in a single world ontology, again, in the kind of picture that you might have had pre-Everett, well, there's only presumably one future you. It would be reasonable to suppose that the conscious experiences that I'm having right now will continue into that future me. The future me's eventual experiences will eventually be my experiences. So I have a pretty strong stake in that future me being happy, being healthy, winning bets, whatever. In the many worlds ontology, however, there are uncountably many future copies of me. And it's made very clear by people who describe the Everett approach, including Wallace. There's no sense of counting copies or counting branches. It's kind of an ill-defined question. Well, the issue is that there's uncountably many copies, and because of, well, the possibility of radically different atomic configurations, which in the Everett approach isn't just a possibility, but an actuality, well, there's going to be copies of you who differ radically from you right now. So there'd be some copies that are similar to you, some copies that are a little bit different, some copies that are radically different from you, down to their atomic configurations. There's nothing that singles out any one copy over any of the others. So it's sort of a bit unclear whether my assumption that I'm just definitely going to continue, my conscious experience is going to continue, makes sense, in which we've sort of broken that question of uniqueness. There isn't a unique me. I'm no more one of these copies than I am any others. Some of them may be radically different from me. So in what sense should I care about these copies? Should I only care about the ones that are similar enough to me? What about the ones that are very different from me? Some of them might be as different from me as a stranger would be. And I hope you'll care about strangers. I like to care about strangers. I think it's important to value the lives of others. But this is now becoming a little bit uncomfortable. So this is a conversation I'm pretty sure I've seen somewhere. I'm almost sure I've had it, but after all these years, I can't really remember. So consider person A. Person A says, I regard the teleporter problem as a serious problem. I don't believe future copies of myself are me in the ways that matter, at least that matter for the purposes of these arguments. So I don't accept any of the Everettian interpretations. Now, person B is an advocate of the Everett approaches. Person B says, well, look, if one of the Everettian approaches is true, then you're being copied all the time. Hence, you must be mistaken about the teleporter problem. And if you're mistaken about the teleporter problem, then you don't have a valid claim against the Everettian interpretations after all. But isn't it sort of trivial to conclude directly from the premise that one of the Everett interpretations is true, that person A is incorrect to reject the Everett interpretations? And in what sense is it a convincing argument to go from the premise my claim is true to the conclusion you are therefore wrong to reject my claim? This argument assumes as its premise the very proposition to be argued for. And I'll argue that this is a pattern. So another analogy that comes up a lot in treatments of the Everett approach is an analogy to Copernican cosmology, which you could view as a somewhat more nuanced version of the argument I just presented. And it appears all the way back in at least the abridged version of Everett's 1957 thesis, The Relative State Interpretation of Quantum Mechanics. So just to give a brief qualitative description of what's going to happen here, the idea is that you take your premise to be, my theory is just as good at predicting your experience as your theory is. And from this, one should conclude you're therefore wrong to reject my claim. This is from the abridged version of Everett's thesis. He writes, arguments that the world picture presented with this theory contradicted by experience because we're unaware of any branching process. Of the criticism of the Copernican theory that the mobility of the Earth is a real physical fact is incompatible with a common sense interpretation of nature because we feel no such motion. In both cases, the argument fails when it is shown the theory itself predicts that our experience will be what it in fact is. In the Copernican case, the addition of Newtonian physics was required to be able to show that the Earth's inhabitants would be unaware of any motion of the Earth. And we'll return to that last point shortly. It's very, very important. And it is to Everett's credit that he made that point very clear. Everett also brought up this analogy in that 1957 letter of response to DeWitt. And this is exactly the same statement. I'm just calling your attention to this particular set of statements. A theory which involves motion to the Earth is not difficult to swallow if it is complete enough theory that we can also deduce that no motion will be felt by the Earth's inhabitants, as was possible with Newtonian physics. Okay? Thus, in order to decide whether or not a theory contradicts our experience, it is necessary to see what the theory itself predicts our experience will be, and especially this point, if it is a complete enough theory. And that is the issue. So this example evolved a little bit. At some point, it turned into a quotation from G.E.M. Anscombe, a quotation from her 1963 introduction to the Tractatus about an exchange she had with Wittgenstein. This is a bit of a long quotation. I'm just going to briefly say, she runs into Wittgenstein. Wittgenstein asks, why did people think it was natural that the sun went around the Earth rather than the Earth turned on its axis? And she said, well, because it looked that way. And he said, well, but what would it have looked like if, in fact, Earth was turning on its axis? And actually, there's a very important second part to this, because Anscombe, she replies, well, I mean, people would have thought they could feel the motion, right? She holds out her hands, her palms upward, goes in a circular sweep, leans backwards, assumes a dizzy expression. People weren't simple-minded. People didn't think that Earth was turning because they thought they could feel it. And it's actually not obvious that you shouldn't be able to feel it for reasons I'll come back to this point in a moment. So this anecdote showed up in a Tom Stoppard play, and then it reappeared maybe between 1963 and 1994, but certainly it appeared in a 1994 lecture by the Harvard physics professor Sidney Coleman, in his lecture, Quantum Mechanics in Your Face. And he recounts this story, unfortunately, with Anscombe erased from the story, which is unfortunate. It's just now a friend who talks to Wittgenstein. Then there's an epigraph from David Wallace's 2012 book. He just says, what would it have looked like if the Earth had gone around the sun? This slightly changes the story a little bit. Now it's not the Earth turning anymore, it's Earth going around the sun. And then Sean Carroll, in his 2019 popular book on the Everettian interpretation, This Is Something Deeply Hidden, restores the full story and gives a more accurate rendering of the story and brings back Anscombe back into the story. Okay, so this is obviously a very favored analogy, but what's the difference here? Well, again, pre-Newtonian people can hardly be blamed for thinking that, that they should be able to tell if Earth were moving. And it takes some non-trivial calculation to show that humans shouldn't feel that motion, but for example, Foucault pendulums should. Right? That's a kind of a nuanced thing. It's not that the effect is completely undetectable or unobservable by people. It's just that humans typically won't experience it unless they set up sufficiently careful experiments, and then you can see it very directly. There's a wonderful museum exhibit at the Museum of Science here in Boston where they have a Foucault pendulum just going back and forth all day. And you visit the museum at the beginning, you come back a few hours later and you see that it's in a different place. Okay, but importantly, yes, it was non-trivial. But at the same time, those calculations are just a few lines of vector calculation. I give them as a homework exercise when I teach intro physics, right? It's not obvious, it's not totally intuitive. Anything involving rotational motion is going to be a little bit counterintuitive, but it's not a hard calculation and it can be done very rigorously. An outstanding issue for the Everett interpretation is whether one can show in a few lines or even a few hundred pages whether Everettian interpretations imply that humans should in fact have the correct experience. And again, I've highlighted that many times. I hope it was very clear. I'm getting a little bit of feedback, sorry, in the audio. Sorry about that. It seems to be better now. So, that's the question at issue, right? And again, Everett, to his credit, was very clear that that's a test that the theory will have to satisfy. Newtonian physics came in and was able to account for the fact that we don't feel the motion that was in the Copernican model. And the question is whether that can be done in the Everettian approach. We'll come back to this example after talking about probability. Now, here's my suspicion, and this is a little bit unfair because I can't read anybody's minds. But here's my suspicion, at least about maybe some people who learn about the Everett approach, maybe people who don't have a very nuanced, complex understanding of it. I suspect that some people who take it seriously are relying implicitly on a notion of Hexaides. That's a bit of a controversial concept in philosophy and metaphysics. Hexaide is basically a thisness. It's something beyond the physical properties of an entity, beyond its outward appearance, beyond its nomological connections, beyond how it interacts with the world, that identifies it as a unique thing compared with maybe something else that has the same outward properties and relationships. So, I think maybe naively, intuitively, the idea is that maybe layered on top of all the many branching copies of your future self is a kind of indicator, that's the Hexaide, that says this specific chronological chain of copies in this branching pattern, this particular chain, this particular branch extending into the future, that one is you, that's your actual branch. And that which branch is selected it's according to the Born rule. So the Hexaide is kind of like a random variable being assigned according to the Born rule. Of course, if you're going to take that point of view, why bother keeping all the other branches in the ontology at all, rather than regarding them as mathematical abstractions? And this is somewhat reminiscent of arguments about modal realism, about David Lewis's modal realism, between people who took modal realism in a sort of a weak sense, argued that there's the real world, there's possible worlds, but worlds in a much more general sense than Everettian branches. And that the possible worlds existed in some abstract sense, but not as concretely as the actual world, versus those like David Lewis, who maintained that the other possible worlds, the other possible four-dimensional stories of everything, were just as real as our world, and that all that made the actual world was an indexical question, that we're just calling it the world that we're in. Denying the existence of these Hexaides is the sort of fine print that I'm not sure many newcomers to Everettian interpretations are aware of, right? You really have to throw this out if you want to align with standard Everettian approaches. There is no Hexaide, there is no special indicator. All these copies are equally you, even the ones that may be physically very different from you. This leads me to a kind of dystopian picture of a possible future. Imagine with me a distant future in which that teleporter technology I described, it really exists. It involves approximate copying of atomic configurations. I say approximate because there's a theorem, the no cloning theorem, that says you can't make literally perfect copies of arbitrary quantum states, but we make approximations to some reasonable level of precision. Would the inventors of this technology go around trying to convince customers, step aboard, don't worry about the teleporter problem. After all, we're all Everettians, right? We're not worried about not being our future copies. You're being copied all the time. So making a copy in this teleporter machine is really nothing different. You should just step on the machine. Would you step aboard? If not, you should ask yourself, why not? Okay, now let me talk about the problem of probability.
which is, arguably the steepest problem faced by Everettian approaches. I have an appropriately evocative example. Okay. All right. So it's an old problem. Everett himself attempted to address this problem in his 1957 long-form dissertation, but his approach also showcased many of the issues that continue to undermine arguments that claim to solve this problem. What is the crux of the problem? The crux of the problem is you can't get blood from a stone, right? That's the metaphor, right? If there's not blood in the stone already, you can't get it from the stone. John Norton has repeatedly, in my press, has stated it in this way. He says that, look, in any deductive argument, your conclusion can never be stronger than your premises, right? A deductive argument involves taking premises, the things that we're taking as givens, and then using sound logic to arrive at a conclusion, but the conclusion must be inherent, at least maybe in some implicit or scrambled form in the premises. So if you're claiming that you've derived an ought from an is, right? This is the ought-is dilemma from David Hume, that, given descriptive statements about the way things actually are physically or questions of fact, you can somehow derive an ought, a normative statement about what you should do or should not do. If you're claiming you've done something like that, or in somewhat more relevant to the present case, you're claiming to have derived a tends to, like a probabilistic statement, from does, from non-probabilistic statements. And those particular choices of words are carefully chosen because they appear in David Deutsch's paper from the 90s in which he claims to have accomplished just this. Well, then you've snuck in probabilistic assumptions somewhere in your argument. Trying to get around this obstruction is like trying to invent a perpetual motion machine, square, circle, or trisect an angle. If someone sends you a letter saying that they've invented a perpetual motion machine or squared the circle, unless they explain clearly at the outset of their paper what magic gives them this power, how they're able to escape this obstruction. If they just send you like a 30-page manuscript with no explanation at the beginning about how they get around the problem, you would be justified in not spending the time to carefully read it. You can assume it breaks down somewhere. So here's an example of a good deductive argument, okay? So let's see what a good deductive argument in this context looks like. Let's suppose the Born rule is the correct probability measure for quantum systems. That's a premise now. We're assuming the probability rule, the Born rule, you take absolute value squared of wave functions, you take trace of density operators times projectors, whatever formulation of the Born rule you like. We take that as our premise. Well, then it follows from standard mathematical and statistical arguments. I can't replicate them here, but you can fill in the blanks because it's just a series of mathematical statements. You can show that the Born rule is positive. You can show it's additive in whatever senses you care about. Additive, say, over appropriate, combinations of Hilbert subspaces and whatever picture you want. That it has many familiar mathematical features that you like. That leads to rational betting strategies. It yields standard decision theory, mutatis mutandis, with any necessary changes imposed by the fact that the rules are quantum and not classical. Provides a typicality measure for trajectories. These are used to great effect nowadays. So this is a deductive argument. We start with premises and we reach conclusions. The conclusions are complicated, they're non-trivial, they're very rich, but they're of course inherent in, ultimately in the premise that we started with. Okay, well, all attempted deductive derivations or proofs of the Born rule and Everettian interpretations try to establish the converse of this argument. They take the conclusions and they try to work backward to arguing that the Born rule is therefore the correct probability measure. This is a formal logical fallacy. It's called affirming consequent. From the logical statement, if P then Q, it does not follow deductively that if Q then P. That's the converse statement. Now, it may be true. If P then Q, well, that may be evidentiary support for the statement that if Q then P in the sense of an inductive argument. Okay, but unfortunately, inductive arguments cannot come to the rescue. Okay, if deductive argument cannot off the ground, what about an inductive argument? The conclusion of an inductive argument can be stronger than its premises or evidence. In fact, this is science, right? In science, we look at a limited number of examples
then we project from those examples to a general theory. That's formally speaking a deductive fallacy. You can't conclude from a finite number of examples a general rule, but we do it all the time. That's induction. And Hume pointed out that this was difficult to justify, or maybe even impossible to justify, but we certainly do it. And nowadays we accept that you can make inductive arguments, and they in fact can have conclusions stronger than their premises. Well, let's follow this and see if it works. So if the Everettian interpretations are incorrect, well, then nothing more needs to be said. Otherwise, they're correct, and we're all copies of observers in an Everettian multiverse. An inductive argument considered by such an observer would entail, and this is important, like all inductive arguments, some probabilistic credence in its conclusion. That's how inductive arguments work. You don't establish the conclusion definitively. Your premises form evidentiary support, and then at the end, you raise your credence, your probabilistic assignment of a credence about what the conclusion is. But probabilistic credences are the thing we're trying to derive. So we run directly into the circularity again. Everyday observers can't borrow probabilities in order to justify inductively that they should be using probabilities. It's circular. And this is, you can see why this is special to the problem of probability itself, right? This doesn't attach to maybe other inductive arguments. Here's a successful example of a deductive-inductive pairing. Right, let's see how they could actually work together to support a physical theory. If you start from the premises of Newton's laws of Newtonian gravitation, that's our set of premises. With a few lines of rigorous vector calculation, you conclude deductively that humans shouldn't feel Earth's motion. It's a callback to discussion before, but Foucault pendulums should. And we can also make many non-obvious, readily testable predictions that would be false based on competing theories. Okay, so that's a deductive argument. We've, from the premises, deduced these things. Once we've empirically verified those predictions, they become evidentiary support, and then we can make an inductive argument that we should accept Newtonian physics with high probabilistic credence. But notice, the inductive argument and the use of probabilistic credence doesn't depend on Newtonian physics, right? So we're not running into any circularity here. This is a valid deductive-inductive pairing. Importantly, you only need a few lines of rigorous calculation in order to establish the deductive conclusions of this argument. We don't have a counterpart of that in Everettian derivations of probability. Again, probabilistic credence is unavailable in Everettian derivations of probability. Importantly, the Newtonian argument contains lots more than just humans don't feel the effects. There are also positive statements about Foucault pendulums feeling the effects, which we can directly observe. You can even stand on a Foucault pendulum all day and gradually notice that you're moving. And of course we can make many non-obvious readily testable predictions that be false on basic competing theories. So here's some common issues that show up in Everettian proofs, so-called proofs of the Born rule, which are inevitable. I mean, there have to be some issues here, but I'm just to be super concrete, point out explicitly what some of them are. Sometimes you're assuming that terms in a superposition are experienced probabilistically in the first place, which already assumes that we're talking probabilities. Or you're assuming that unary, that's unary, not unitary, unary and also binary operations in Hilbert subspaces have logical meanings. So for example, taking Hilbert subspaces, taking their union and taking the vector space closure of that, or taking intersections of Hilbert subspaces and so forth, or acting, projecting down Hilbert subspaces, that these have logical meanings, they're not merely mathematical constructions. 3 is assuming that a purely mathematical function obeying mathematical axioms that mathematically resemble subject to the previous assumption, because some of those resemblances rely on certain assumptions about the logical meaning of operations in Hilbert subspaces. That because you have these mathematical functions, they obey mathematical axioms that resemble those of probability functions, that therefore they are in fact experienced as probabilities. 4 is assuming that superpositions, state vectors involving superpositions with identical sets of amplitudes, those are the coefficients appearing in the superpositions, that if they have identical sets of amplitudes, then there will be correspondingly identical sets of probabilities. 5 is assuming outright that the correct probability function should be a function of the amplitudes to begin with, which is highly non-obvious. Why should we care about the number sitting out in front of our state vector, which we can't directly see? 6 is assuming that finite trial sequences, and in everyday realistic experience, you're never going to do more than a finite number of experiments on any particular question, are somehow constrained by the behavior of unphysical infinite limits of trial sequences. This is a problem even beyond the Everettian approaches for certain frequentist approaches to the theory of probability. Assuming that if you force an observer to take a stand and make a bet, you can conjure probabilities into existence just by demanding this. David Albert, I think, puts this very colorfully. If you hold a gun to my head and tell me to make a choice, I tell you that you're not being very nice. 8 is otherwise assuming implicit probabilistic notions in one's premises and axioms. And 9 is assuming certain unjustified idealizations. That's a major problem that I'll come back to later. So this is a non-exhaustive list of examples. Everett's original dissertation commits 1, 3, 5, and 6. Deutsch's 1999 attempted proof of the Born rule. Quantum Mechanics of Decisions and Probability, I think it's the title, commits 1, 3, 4, 7, 8, and 9. Wallace's marvelous 2012 book-length treatment contains 2, 3, 7, 8, and 9. And, there's a cliche that, physicists who doubt the existence of measurement problems say, oh, I could explain how to fill in all the gaps. If I just find an hour to sit down and write it all down, I'm just super busy. This cliche seems less common these days. I think we all particularly owe Sean Carroll tremendous credit for years of skilled and time-consuming engagement both within the physics community and beyond, for making clear that problems of understanding quantum mechanics are serious problems. We should take them seriously. We shouldn't regard them as trivialities. But the larger lesson still stands. Sometimes gaps can't be eliminated because they're telling us something important. It's not an accident that those gaps are there in those other treatments. They have to be there because they're trying to do something that you can't do. Let me talk now about some newly identified challenges. So putting those sort of older, ongoing challenges aside. Okay, I call this next problem the problem of isomorphism. Let me explain what it is. So here are 2 distinct claims that are often elided in the literature on Everettian approaches. The first claim is that quantum theory without the collapse postulate gives an empirically adequate description of physical reality, maybe even the most empirically adequate description possible. Maybe you could argue that not only is it empirically adequate, but there could not be a more empirically adequate description. There are some other principles that say we can't possibly know more about the universe than quantum mechanics can give us. Okay, so empirically adequate description of physical reality. The second claim is that quantum theory without the collapse postulate is isomorphic to physical reality. Okay. Now, being isomorphic to physical reality is different from simply providing the best, or maybe not the best, but a very good physical description. Many people, Bohmians, modalists, people who subscribe to modal interpretations, people who subscribe to the Platonic interpretation, among others, who reject Everettian interpretations, agree with the first claim. Everettians are not unique in agreeing to the first claim, but disagree with the second claim. Blurring the distinction between these helps sell Everettian quantum theory, making it seem more inevitable. Right? Because if you blur the distinction and you accept that quantum theory gives an empirically adequate description, it makes it seem inevitable that you have to accept that it's an isomorphism with nature. I'll return to this issue of branding later. Taking quantum theory literally or seriously is therefore an ambiguous statement that makes Everettian interpretations seem more inevitable than they actually are. You can find examples of this in Wallace's book. He says, really, the Everettian interpretation is just quantum mechanics itself, read literally, straightforwardly, right? If one really takes quantum mechanics seriously, then the various terms in a macroscopic superposition must be taken as describing physically real macroscopic worlds, which for all practical purposes are not interacting. He says, DeWitt, he's just paraphrasing DeWitt's article in Physics Today, 1970, he recognized that quantum mechanics taken literally tells us the macroscopic, approximately classical world we observe around us is only part of a far larger reality. So here's actually an important case study from classical physics to highlight the distinction I was making here. In a 2014 paper, Eric Carroll argued rather beautifully, it's a very beautiful paper, I highly recommend it, that classical physics is in a precise sense isomorphic to the Lagrangian formulation, where by Lagrangian formulation, I don't mean, because you might ask, what about dissipative forces? What about if you can't write down a Lagrangian? He meant the sort of geometric mathematical framework of tangent bundles that we use to describe systems in the Lagrangian formulation. He argued that classical systems are in a precise sense isomorphic to that formulation, but not to the corresponding mathematical geometric formulation one uses in the Hamiltonian picture.
Now, one of the virtues of the Hamiltonian formulation is its very flexibility. We can take the position of a particle, its momentum, we can redefine them by mixing the two concepts together, so-called canonical transformation. We have a tremendous amount of flexibility in relabeling and redefining the basic variables at play. And that makes it very convenient for solving problems that might be difficult to solve in other ways. But it also means the Hamiltonian formulation, that very flexibility means it lacks some of the structure in the underlying classical system. Does this mean the Hamiltonian formulation is an incorrect description that is empirically inadequate, or that we shouldn't take it literally or seriously? Of course not. Right? It's very empirically adequate. We use it all the time. We're not saying it's wrong in any way. Right? And nor is classical physics or this Lagrangian Hamiltonian story unique in this regard. We think classical probability theory is perfectly empirically adequate as long as you're talking about the classical world. But we don't then go further and declare that therefore it must be isomorphic to the real world, that probability distributions are isomorphic to physical things in the real world. Right? That's a distinction that we see in other theories. So after you mod out, meaning that you regard as equivalent, so you regard, state vectors or the universal wave function or whatever as equivalent up to global constant unitary transformations, the Everettians claim that the mathematical formalism of quantum theory is isomorphic to physical reality. Again, this is a non-trivial and distinct claim from merely asserting that it's an empirically correct formalism. One runs the risk that there could be mismatches between the mathematical formalism and physical reality, beyond the level of empirical predictions. Again, see the Lagrangian versus Hamiltonian case. These mismatches could betray the existence of hidden or additional variables, or maybe more subtle structural discrepancies, again, as in the Lagrangian Hamiltonian case. The lack of a persuasive justification for this claim is the problem of isomorphism. How do you get from merely saying, yeah, I'll take as a premise that it is the correct theoretical description of reality, that it's actually isomorphic to reality? That's the problem of isomorphism, how you make that jump. There's some causes for worry. We already know of several ambiguities in the mathematical formalism of quantum theory that could make us suspicious. For instance, there's the famous problem of inequivalent representations in algebraic quantum field theory. A quantum field theory can have unitarily inequivalent representations. It's not clear which of those is supposed to be the true one. But as we'll also talk about later, there are these so-called local and time unitary transformations that we need to worry about that can radically change what your stories look like in Hilbert spaces. There are even more radical changes to representation. You can do quantum mechanics with only the real numbers and have a formalism that is just as complete as standard quantum mechanics. But it looks a little less separable than what you'll find in the sort of complex representation of quantum mechanics. But it does look qualitatively different. There are no pure states if you do the real approach rigorously. So it does look like a qualitatively different mathematical formalism. And then what of the ongoing debate over algebraic imperialism versus Hilbert space conservatism? Do you define the quantum system by its algebra, the algebra generated by its observables? Do you take a quantum system to be defined by a particular Hilbert space, especially if there may be different unitary line equivalent Hilbert spaces? Is reality isomorphic to all of these things? It's not quite clear how to proceed. There are a lot of advantages to not asserting that it's an isomorphism. For example, Fell's theorem is essentially a theorem that says that many of these distinctions empirically don't make a difference. But if you insist on there being an isomorphism between physical reality and the formalism, you have to make empirically underdetermined choices. And this seems like a serious problem. All right, the next problem is what I call the problem of Newspeak. So this is actually brand new. This comic just came out. Take a moment. Okay, so I'm going to move on. All right, what do I mean by Newspeak? So, many of us are probably familiar with George Orwell's 1948 novel, 1984, about a dystopian, what was to him his future. The purpose of Newspeak in his, terrible totalitarian imagined future society, Newspeak was created by the government to simplify language for the purpose of conflating concepts, constraining the ability for human beings to think about things, and to make some ideas seem more inevitably true as a form of propaganda. Now, some of this use of what I would argue is a form of newspeak predates the debate over Everett interpretations. Consider the common and, in most cases, innocent conflation of state with state vector. People say, oh, that's the state of the system. Well, it's a state vector representing something about the system. It's empirical content or whatever.
but simply calling it a state is a convenient shorthand, but it actually constrains thought. It can make it hard, especially for seasoned quantum mechanicians, to regard states as conceptually different from state vectors or wave functions. Another example is the conflation of hidden or additional variables with local hidden additional variables, which makes it seem like the Bell, CHSH, GHZ theorems proved more than they did. You see people literally say, I see this in papers, oh yeah, Bell showed there can't be hidden variables. There just can't be. Well, he showed there can't be local hidden variables, dynamic local hidden variables. Conflating the two concepts makes it seem, makes it difficult to see the distinctions there. Another is the conflation of non-local influences of a subtle, non-directly controllable or observable nature with non-local signals. People will say, well, there can't be non-local signals, so all non-local hidden variables theories are clearly false. Well, you're conflating two different kinds of non-local effects, one of which we can observe and should be ruled out because it can lead to apparent causal paradoxes, and the other doesn't lead to causal paradoxes. All right, but now about Everettian approaches. Okay, to be clear, I'm confident this problem of newspeak among advocates of Everettian interpretations is unintentional. I'm not assuming any ill will anywhere, but it is something I think people should be aware of and hopefully try to avoid doing. So one significant example that's widely read among physicists, I've actually had physics professors say, oh, there's no problem with quantum mechanics. Just watch this lecture that Sidney Coleman, the Harvard physics professor, gave in 1994, Quantum Mechanics in Your Face. He solved all of it. I've heard multiple physics professors say that. Well, Coleman clearly employs an Everettian interpretation. He says explicitly, the position I'm going to advocate is associated with Hugh Everett in a classic paper. But then he refers to this as quantum mechanics stupid. Literally, he says those words. He just calls it quantum mechanics. Wallace's book, again, says really the Everett interpretation is just quantum mechanics itself, or just unitary quantum mechanics, or just simply quantum mechanics. Why even bother calling it Everettian quantum mechanics? It's just too linguistically difficult. Okay, I would argue that we should stop that. Okay, next problem I'm going to talk about is the problem of skepticism. So maybe take a moment. But everything's just signals in my sensory cortices. How can I be sure they correspond to an external world? Okay, so here's a fictional exchange. Person A says, it's raining. You don't have an umbrella or raincoat. You're all wet. Person B says, wetness isn't real. It doesn't exist. Person A says, what do you mean? How could it not be real? And person B says, what we call wetness is only an approximate convenient description. At the level of the microdynamics, where there are just individual water molecules, there's no fundamental definition or meaning to wetness. Atomic force microscopes don't see wetness. Person A says, all right, I grant you that wetness isn't fundamental and that it supervenes on microscopic ingredients that don't individually exhibit wetness, but emergent entities can still be real. Things can exist without being fundamental, but granted, it's not absurd to take the opposite view. This is an arguable point. Okay. So I'm setting this up as a contrast for what we'll see in just a moment. Let me talk a little bit about some definitions. I'm going to call a weakly deceptive physical theory one that implies that at least some of our observations are deceiving us. For example, the molecular theory of water, I just gave an example, tells us that our eyes are deceiving us about the fundamentality of wetness. But molecular theory of water would not tell us that atomic force microscopes are being deceived. Essentially, all our successful physical theories are weakly deceptive to some degree and others. This is really just a question of degree. A strongly deceptive physical theory, I'll take that to mean one that implies that all of our possible observations, past, future, forever, about some whole class of phenomena are deceiving us. So here's a premise to consider. Other things aside, we should generally prefer physical theories that are strongly deceptive about fewer or no classes of things to physical theories that are strongly deceptive about more classes of things. Now, yes, nomological simplicity, dynamic locality, those also matter in evaluating whether we should accept a physical theory or interpretation, but I would argue there is something pushing the other way. Strong deception is something we should take into account as being on the other side of the scale, because in a way, it's a narrow form of radical skepticism about our experience. Who are you going to believe, Everett, or your lying eyes, telescopes, optical microscopes, atomic force microscopes, ... Here are some things that we empirically observe at the microscopic level, and sometimes also the macroscopic level. We observe definite measurement outcomes. We see them at atomic force microscopes too. Indeterminism, stochasticity. We abjectly experience these things, whether we're looking at microscopes or with our eyes. Non-local correlational phenomena, but without controllable superluminal signaling. the practical incompleteness of the formalism of quantum theory for predicting what specific outcome we'll empirically observe. You're using a super powerful microscope, you still can't predict what the outcome is going to be. And a crucial observed behavior of probabilities that I'll elaborate on in just a moment. These are 5 things that we experience at all levels of description, at least microscopic levels of description. We have no reason to doubt that they're part of reality. Everettian interpretations deny all of these basic empirical experiences in all situations and by all empirical observational equipment, forever and ever. In their place are in principle unobservable things like Hamiltonians, a unit norm universal state vector, and on some Everett interpretations, a preferred set of operators. Descartes' demon, right, in his thought experiment of the demon who's fooling him, deceiving him, sending his brain sensory images that aren't real, that demon would blush at this. This is what I call the problem of skepticism. It's not that we should never accept a theory like this. It's not that we should rule it out, but certainly we should ask for very strong evidence that this is the only way before we accept this level of radical skepticism. Now, let me get to that point 5 about this observed behavior of probabilities that's denied by Everettian interpretations. This is inspired by a talk that David Albert gave at my 2020 mini workshop on Everettian quantum mechanics. So here's a feature of probabilities that we empirically observe all the time and which underlies all of empirical science. If a bounded number M of scientists attempt to test a raw numerical or probabilistic prediction X of a correct physical theory, so imagine M scientists, right? They have a physical theory, they want to test some prediction, it could be numerical, it could be probabilistic, call that prediction X. Well, then they can make their empirical results match X to any desired level of accuracy by taking the number of trials N to be sufficiently large. If their results haven't converged closely enough, they just increase the number of trials. If the theory is correct, then empirically our experience is their results will converge on that answer. Okay? Beware that none of these statements can be dropped. Every one of these statements here is crucial for this to get off the ground. Okay? It is our robust empirical experience that probabilities work this way, and it makes all of science and more possible. Now, admittedly, we lack a consensus metaphysical theory of probability that accounts for this empirical behavior. The different schools, of probability. Should we be Bayesians? Should we be frequentists? Is there some philosophical orientation of probability that explains why probabilities do this? We don't have a theory of that, but this is our empirical experience, and Everettian interpretations deny that it's true. From Wallace's book, he specifically says, well, if someone says, I require this of probabilities, he says, what is your evidence for believing probabilities require this? And I would argue empirical observations arguably count as evidence. So in his 1970 article, DeWitt noted that Everett interpretations contain so-called Maverick worlds. Right? All the worlds are there, even those in which everything goes wrong and the statistical laws break down. He argued circularly, which is kind of funny because he mentions that he's trying to address a claim of circularity, as you can see in the first paragraph there under Maverick worlds. He argued that you can dismiss those Maverick branches because of the extreme smallness of the portion of the Hilbert space that they occupy, meaning you can ignore them because their amplitudes are small, but that assumes the very thing to be derived, that small amplitudes means that they're negligible, that they're unlikely. In fact, according to Everettian approaches, increasing the number of trials generates more Maverick branches. Observers in these Maverick branches disconfirm the predictions of the Born rule, thereby falsifying quantum theory itself. And yet somehow, as a matter of robust empirical experience, we never find ourselves in such Maverick branches. Now, the non-Everettian has already answered why we don't find ourselves on Maverick branches. We don't find ourselves on them because they don't exist. The Everettian doesn't have that escape. The Everettian has a different answer. We aren't on one of those Maverick branches because if we were, then we wouldn't be asking why we aren't on one of those Maverick branches, which seems a little bit circular. Or maybe we could make a Dutch book argument. I'll come back to that in a moment. Problem of idealizations, which is connected to the problem of the Maverick branches. Any sound argument for dismissing Maverick branches cannot legitimately ignore their ubiquitous presence on pain of circularity. This is the problem of idealizations. That is, if you want to argue that we could ignore Maverick branches or argue more broadly that for probabilistic interpretation of the amplitudes of superpositions in the Everett approach, you can't ignore the Maverick branches because to argue the Maverick branches are unimportant is what the argument is supposed to generate as its conclusion. And yet the usual arguments
for deriving the Born rule in Everettian approaches employ idealizations that ignore undesirably extreme Maverick branches. So Wallace's book, he says, you know, how do we get this off the ground? Well, you can justify that we use the Born rule because a bettor, someone making bets who doesn't use the Born rule against an opponent, the opponent can guarantee a win, can guarantee that the person making the bets will lose money. Okay? So this justifies, well, if you want your descendants, if you consider them seriously as copies of yourself, to not necessarily lose money, then you should use a betting strategy that corresponds to the use of the Born rule. But what about extreme Maverick branches? What about the branch in which her opponent just decides to hand her all the money, then runs off and joins the circus, and then, I don't know, turns into a chicken? Those branches exist. They're there. Aren't we taking quantum mechanics literally and seriously? Right? Those weird outcomes are there. There's no way to guarantee that if you don't use the Born rule, you're definitely going to lose money. That's impossible. I think this is illustrated quite nicely in this comic. Miklos, I'm almost done, so I just need a few more minutes if it's okay.
Well, yeah, we are in the 60th minute, so
I'll be quick. Yeah,
be fast.
I'll be fast. So this is illustrated, I think, in this lovely comic, right? So here's Schrodinger doing the experiment, and then rather than seeing a cat that's alive or dead, he sees an angry monkey, right? That's a Maverick branch. Okay. Now we use idealizations on their physical problems, but in those cases we have prior notions for what it means for the discrepancy to be small and therefore negligible. In trying to derive that amplitudes or experiences probabilities in Everettian interpretations, the smallness of those amplitudes is itself the question up in the air, so it's not clear what it means or why it's justifiable to treat them as negligible. That's a fundamental obstruction to these sorts of idealizations. Okay, I'm gonna have to summarize. There's just a couple of slides left. This is a slide on the whole problem, which just says that one of the challenges to taking space-time seriously as an ontological entity is that you can do a certain kind of mathematical transformation. You can transform it without changing any physical predictions, and therefore physical observable things do not, underdetermine. Physical observable predictions underdetermine a specific choice of space-time and metric. This is known as the whole problem for historical reasons. There is a counterpart in quantum mechanics of the whole problem. You can reformulate the Schrodinger equation as a gauge invariant equation of this form with this particular definition upper. This is just a rewriting of the Schrodinger equation. And then you see that the Hamiltonian plays the role of a so-called flat gauge connection, a 0 + 1 dimensional gauge connection. Then there exists a completely analogous set of transformations, first, I think, noted by Harvey Brown in 1999, that have exactly the form of a non-abelian gauge transformation. This is completely analogous to the kinds of mathematical transformations one has in the GR whole problem. So I call this the quantum mechanical whole problem. Right. Similarly, the quantum mechanical whole problem, just like in the GR problem, undermines space-time substantivalism. The quantum mechanical whole problem undermines state vector Hamiltonian substantivalism. And severely for mad dog Everettianism, which says that all you have is the Hamiltonian and the state vector. Well, because we're not positing any gauge invariant observables, the only positive structure is akin to the space-time manifold and metric. It's pure gauge. If two quantum Laplace demons who can see the state vector from the outside happen to be using different state vectors and different Hamiltonians that are isomorphically related by one of these so-called local in time gauge transformations, they have two isomorphic pictures, but in their pictures, they have different evolving state vectors with different branching patterns. Who's right? Who's describing reality? I mean, after all, these pictures are isomorphic. Wallace gets around this problem by specifying that additional structure by providing the gauge invariant observable. So arguably, he evades this problem. The final problem is a problem of discernment, which is just the question of which patterns am I going to take seriously in Everettian approaches? Okay, so this is more than just how do we show that structures like people and galaxies and buildings can be derived from the Everettian ontology. Which patterns count? In the Mad Dog Everettian approach, there's no statement about which particular configurations of things count. In Newtonian mechanics or Bohmian mechanics, right? As long as, well, at least in the versions that treat the wave function homologically and just say the ontology is just consists of particles, we know what it means to say that you have a particular physically instantiated pattern, some arrangement in space of the particles. We call that, an emergent object of some kind. In the Mad Dog Everettian approach, there's not a clear statement of which particular things are to be regarded as patterns, right? The ontology is specified only as an equivalence class of unit norm state vectors and unitary equivalence.
And things like tigers or people are purportedly emergent patterns in the universal wave function, but in what precise sense? Which patterns are admissible? How do we discern the right kinds of patterns from the wrong kinds of patterns? If I've got a hula hoop instantiated the universal wave function, and I calculate its circumference over diameter ratio, essentially pi, but I allow maybe the hoop to slightly change shape with time, well, then the decimal representation is going to contain patterns in it that are maybe the binary representation of the configurations of the atoms in a tiger running around. Does that pattern count as one of the patterns? It's not clear which patterns are admissible and which ones are not. All right, so just to conclude, in this talk, I covered a number of challenges to Everettian interpretations. I talked about old ongoing challenges, the problem of identity, the problem of probability, as well as newly identified challenges, the problem of isomorphism, the problem of Newspeak, the problem of skepticism, the problem of idealizations, the quantum mechanical whole problem, and the problem of discernment. Again, my hope is that this generates new work that helps put Everettian interpretations on a stronger footing. So with that, I'll conclude with this final comic. What's on the everything bagel? Everything, literally everything, otherwise it'd be false advertising. Or even tiny everything bagels, because by definition, the everything bagel contains everything, including itself. And my favorite thing, try the Mandel bratwurst. All right, that's it. Thank you.